Okay, clear it, clear. All right, the way your calculator works is a little weird. You have to put the -3 in first. Okay, so type in -3 first. Okay, and then, actually, yeah, there you go. And then hit the green and that button. There you go. Who else? You got it? You need help. Okay, let me look at this real quick. I forgot my glasses, so mode. I may not know how to do this right now because this is a different calculator. 7, 6. I think I got it. Try it again. Try. I did e to the -3. Okay, yes, I don't even know how I did that. So don't ask me to do it again. Okay. You got it? Okay, so what's the next one? What's e to the -2? 0. Sorry. 135. Okay, thank you. And then e to the -1. 0.367. Okay. E to the 0, I can do that. E to the 0 is just 1, because any number to the 0 is 1. And then e to the first power, yeah, it should be what I told you e was, right? E to the first power should be itself, 2.718. Okay, e squared, what's that? 7.389, something like that. And then last one, e cubed. 20.089. All right. Good? All right, so now what I'd like to do is graph it, right? So I'm just going to do a little graph. Again, I don't need to go down with this because I know my answers are always positive. And the biggest one I get is 20 this time, right? So I'll still count by fives. 5, 10, 15, 20. If I go a little past 20, that's okay. And then I'm just going to do 1, 2, 3, and then -1, -2, -3. I like to start out at 0. When I plug in 0, I get 1. When I plug in 1, I get 2.7 something. When I plug in 2, I get 7 point something. See, I'm just like roughly graphing this. 3, I get 20 point something up here. And so I know my graph is going to have this exponential growth. And then over here, I know these get smaller. Notice I'm not really trying to plot these points because it would be really hard for me to plot 0.049. But putting the dotted line here lets everyone know that this is just getting closer and closer to the x-axis. Okay, questions here? The one we did before, right? When we did 2 to the x, we did 2 to the x. We've done that one before, right? We made a table for this one, 2 to the x. It was, if you go back and look, 2 to the x would have given us this. Here we would have been at 2. At 2 we would have been at 4. And at 3 we would have been at 8. And then that graph goes like this and grows. And then it decays down like that as well. This is 2 to the x. This one is e to the x. Which of those is growing faster? The e to the x, right? As you move to the right, the black graph is above the blue one, right? Which means it's growing faster than 2 to the x. If I did 3 to the x, which we did with the bacteria problem, 3 to the x, we did that last class. If we plotted that, here's what it would look like. At 0 it would be 1. At 1 it would be 3. And then 3 squared would be 9. 3 cubed would be 27, which would be up there. And so that graph would look like this. That's 3 to the x. So 3 to the x grows faster than e to the x, which grows faster than 2 to the x. So the bigger the base, the faster it grows. All right? Make sense? Do y'all care to know why e is special? I mean, I can talk briefly about it, but I mean, yeah? Okay, so in calculus, what we're actually interested in calculus is, you know how we've been graphing functions? Like, let me go to a polynomial function. You know how we learned how to graph these polynomial functions and maybe like both sides went down, something like that? We graph them and bouncing and crossing, all that stuff. And remember I told you that you never have to figure out how high something went or how low, just that it was above or below. So don't worry about how high these hilltops are and how low the valleys are, that we deal with that in calculus. The way we do it in calculus is, and this is one of the main points of Cal 1, is that we say, is there a way that I can go to this function, go to any point on it, and find the slope of a line that goes through that point, but is what we call tangent to the curve. So like this line that goes through that point, right? But it's not tangent to the curve. It has to like just touch the curve just barely at that point. So do you all see how that would be a tangent line at that point? And then if I move the point, like if I move the point right here, then my tangent line would look more like this, right? Just barely touching the graph at that one point. Make sense? So in calculus, there's a way to actually find the slope, right? This is a line. We can find m, the slope of this line. So to find the highest and lowest points, what we do is we ask ourselves, where is the slope what? Tell me about the slope of the tangent line at this point. What would it be? What would the slope of the line that's tangent right there be? What's the slope of a line that's flat like that? 0. Down here? 0. Up here? 0. You see? So in calculus what we do is we actually find a way to come up with a formula to give us the slope. And then we ask ourselves, when is that formula 0? And then we have to go solve an equation. That's what we do in calculus, all right? So mathematicians for a long time were wondering, is there a function, okay, that when you actually go, let's say we go to this point right here on this, we're looking at 2 to the x. If I go there, do y'all see the tangent line right there? It has some slope. I don't know what that slope is, right? But mathematicians were asking, I wonder if there's a function that when you go to find the slope, when you're trying to find the slope on the function, that the slope is actually just the exact same number as the height of the function there. So this slope is just that height. And we were like, I wonder if there's a function that behaves that way. And we were looking for it, like right here, what's the value of this 2 to the x? What's the value of that function right there? If I plug in 3 into this, what do I get? 8, right? So if I take this tangent line, the slope of this, I can tell you right now the slope is not 8. But we were looking like, I wonder if there's a function where that slope would be equal to the output there. And we went and looked and looked and looked, and we found one. And this is it. This is the magic function right there. So if I go to the point, I'll do it in red. I'll do it, yeah, in red, I guess. So if I go to the value 2, okay, on this e to the x, let me erase the other ones. If I go to the value 2 on that e to the x, what is the value of this function here? If you plug in 2, what do we get? I erased it. What did y'all get when y'all plugged 2 into the e to the x? 7.389, right? That's how high that point is. Well, guess what? The tangent line, if you put it there, that's also the slope of that line. Like the slope of this line is 7.389. And it works for any point on the graph. So if you go to here, right here, go up here, what's the value of that right there? 2.718, right? When you plug in 1, you get 2.718. Well, if you were to get the tangent line, put it there, it would have a slope of 2.718. And it works for every point. And it's the only function that does that. There is no other function that exists that does that. It's unique, and we can't explain why that does that. So we call it the natural exponential function because it's just naturally that way, all right? There's no rational explanation for it, all right? It just is. Okay, so that's the little side story. We're not going to get into that anymore. All right, so the natural exponential base is one of the important ones because of that property I just shared with you. It's the only one that does that. Now let's talk about the other important base. And just so you all know, at the end of the day, when it comes to sketching, right, for this stuff I'm talking about, the only thing you're going to have to do in terms of sketching is what I've shown you. Make a table, plug in those numbers, use your calculator. If you can do that, you'll get a good grade for that part of the test, all right? Everything else here is kind of ancillary. The second one is the base 10 exponential function. So as you might expect, it's the function f of x equals 10 to the x. Is this exponential growth or decay? Growth, because this number is bigger than 1, right? Does this grow faster than the exponential, natural exponential? It does, right? Why? 10 is bigger than 2.718, right? So this grows really fast, right? Really, really fast. And we can make a t-table. I'll make a quick one, all right? X, 10 to the x, -3, -2, -1, 0, 1, 2, 3. I'm going to go fast here. If I plug in 0, I get 1, because that happens every single time on every exponential function. If I plug in 1, what's 10 to the first power? 10. If I plug in 2, what's 10 squared? 100. 10 cubed? 1,000, right? Now the other way, if I plug in -1, I get 1/10 or 0.1. Plug in -2, you get 0.01. Plug in -3, you get 0.001. And then if you plot these, I can't even put it, well, I could put it, but it's, do you see how fast that grew? I'm at 1,000 when I get to 3. I'm at 1,000 already. So my graph would have to look like, let's see, 1, 2, 3, -1, -2, -3. And then I need to be at 1,000, so maybe I'll count by hundreds. 100, 200, 300, 400, 500. You get the idea, right? Way up here is 1,000. So at 3, I'm way up here at 1,000. At 2, I'm only at 100. At 1, I'm at 10, which is way down here. And at 0, I'm at 1, which you can't even really see, right? If that's 100, 1's way down there. So do you see how quickly this just like shoots off, right? And then this way, it flattens out very fast. You have a horizontal. So when you're watching the news, right, and they're like, COVID is spreading exponentially, or they say, you know, crime is increasing exponentially. That's like, people like to throw that word around, exponentially. But technically, when you say something's growing exponentially, that's not very specific, because you could have exponential growth that's actually not that fast, or really, really fast. Or if you're not even careful, then you could actually be talking about decay, because it could be, your A could be a number like 1/2. So, all right. Why do you think the base 10 is an important base for us? I said there's two important ones. This one I showed you, because in calculus, it's a special function that behaves a certain way. Anyone have an idea of why base 10 is important to us? Any guesses? Yes? Meters? Oh, years. Okay. It's something even more subtle, and it's so obvious it's hard to see. You know, like sometimes things are just so obvious that you don't see them. Let's think about something. This is off topic but on topic. All right. I feel like I've shown you all this before, but if I have, you're going to see it again. 432. If I write that number down, right? If I write that number down, I can look at this as being 3 digits, right? The 2 represents how many whats I have? Ones? What's wrong?
I just got it.
You got it? Okay. So says we have 2 1s, right? And then what does the 3 mean? We have 3 what? 10, so I'm going to say plus, I have 3 10s, right? And then this means I have 4 what? 100s, right? So 432, think of money, right? 432, I could hand you 400s, right? I could hand you 3 10s, then I could hand you 2 1s, and that'd be $432. This is our number system, right? Each digit represents something, right? What you probably don't really ever think about is that this first digit is always how many 1s you have, right? I want you to look at that digit as not, that number is not as a 1, but I want you to think of it as 10 to the 0. Isn't 10 to the 0 1? Right? 10 to the 0 is 1. So you have 2 10 to the 0s. What's 10? 10 is 10 to the first, right? What is 100? 10 squareds, right? What would be the next digit here? Your thousands, right? So if I put a 7 here, that would mean you have 7 what? Thousands, right? 1,000 is 10 to the third. Each digit in our number system, each digit is just a higher and higher power of what? A higher and higher power of 10, right? The next one would be, if I put a 3 here, that would mean we have 3 of these 10 to the fourths. Understand? One more thing. If I give you another digit right here, this is the big key right here. We know that this is going to be 10 to the fifths, right? How many different things can you plug in here? Somebody give me an example of something I could plug in here. 9, okay, that's one thing. What else could you plug in? 4, that's the second thing. What else could you plug in? 7, what else? 3. How many options do you have to plug in here? 10 options. You have 1, 2, 3, 4, 5, 6, 7, 8, 9, right? And 0, right? So in this slot, in this space, you can plug in, you get to pick from this list of numbers. 0, that's a brace. 1, 2, 3, 4, 5, 6, 7, 8, and 9, right? There are 10 choices, right? You have 10 choices on what to plug in to that digit. And whatever digit you plug in from here, that would be how many 10 to the fifths you have. Each one of these you have 10 options, don't you? Okay? Each one of these you have 10 options. I'm going to ask you to imagine a world, okay? Imagine a world where there are only 5 options. Okay? Can you imagine if we had this? Well, let's go with something else. Let's go with 4 options. What if I told you in this new universe that you live in that you only have these numbers right here? That's a 2. Those are the only digits that you ever learn. Okay, you go to grade school, they say, okay, we're going to start counting, right? 0, 1, 2, 3. Those are the only digits you're allowed to use. And when you make a number, let's say we make a 3-digit number, you can only plug one of these 4 into this, all right? So let's say I plug in 2 here. Any guess as to what, like here, we plugged in a 2 here, right? This told us how many 10 to the 0s we have. What would this be telling us? We have 2 whats? 4 to the 0s. Because how many options do we have? 4. Now I could plug a number here. Could I plug 7 in here? No, 7 does not exist in this universe. So I could plug what, 3 in here, and this would tell me how many whats I have. 4 to the 1s. And then imagine I plug another one, like I plug in 1. This would tell me how many 4 to the 2s I have. All right? This is called, this right here, we have 4 choices. This would be called a base 4 number system. But in our number system, we use a base 10 number system. There are 10 options for each digit, and each digit is a power of 10. Why do you think that we use a base 10 number system? Because I'm telling you right now, we could start teaching children to use a base 4 number system and all the math would still work. Why do you think we chose base 10? What? What? Do you have why do you think we use base 10? Any ideas? I mean, because we just accept it, right? We just accept that those are the 10 options. There's no 11th digit, is there? You can't say, oh, well, you could put the number 10 in here because 10 is made up of 2 of those, right? 0 and 1. Like, we don't have another digit. Like, have you ever seen this digit? No, right? That looks completely foreign to you. But it could be our 11th choice if we wanted it to be, right? It could be. Come on, think about it. Any reason why you think that human beings use base 10? That's how many fingers we have. That's it. It's because it makes perfect sense, right? Like we have 10 fingers, we started counting, right? And of course, so if we only had 4 fingers, right? Let's say we had 2, right? Well, first we'd probably be in bad shape. We need an opposable thumb, right? To be able to pick up things and manipulate things. Let's say we only had 2 fingers, right? Then I would be willing to bet my life, okay, that we would be in a base 4 number system. Because this is what would make sense, counting, right? 1, 2, 3, right? That would be it. That would be it, all right? But it's base 10 because we have 10 fingers. And so the base 10 number system is what we use. And so, of course, the exponential function of base 10 is going to be important to us because that's the number system we're in. There's no computer science majors in here, right? But if you were in computer science, a computer, right, uses something called binary. Have you all ever heard binary before? What does binary mean? 2 choices, right? What are the 2 choices in binary? 2 digits, 0 and 1, and that's it. Those are your only 2 choices, and the entire number system is based on that. So in binary, if you make a number, right, let's do a 3-digit number in binary. Let's do a 1 here. I can only plug in a 0 or 1, right? Let's do a 0 here and a 1 there, right? This is how many whats I have. How many options do I have?
2.
So this is how many 2 to the 0s I have. This is how many 2 to the 1s I have. This is how many 2 to the 2s I have. Let me go one step further. What's 2 to the 2nd power? 4. How many of those do I have? How many of those do I have? I have 1 4 plus, okay, how many 2 to the 1s do I have?
0.
None of them. Okay, how many 2 to the 0s do I have? 1. So what's 2 to the 0? 1. So I have 1, 1. So I add to that, that's just 5. So this number in binary is actually this number in base 10. So when a computer sees 101, it knows that's the number 5 to us. Okay, I'm going off. Binary, there's systems with 16 choices. That's called hexadecimal. There's a lot of computer science people will use hexadecimal because we need more options. Yes? Oh yeah, I could keep going more digits. And then each digit I go is just a higher power of 2. Yeah. All right, I've successfully gone off topic. Oh, I'm on topic, but I'm a little bit outside of where I wanted to go. Those are the 2 important exponential functions, all right? Those are the 2 important ones. E to the x and 10 to the x. Yes?
This is off topic, kind of.
Oh, it's all right.
I'm a music composition major.
Uh-huh.
And one thing that's interesting about Western music is that we have 8 notes.
Everything's an 8 count.
But in Eastern music, a lot of times they'll have more than that, and we call it microtonal.
Okay.
Which means that there's more options, so we can get like, it's almost like decimals, to where you have a note that we think is like a whole number kind of, but if you detune it halfway, you can use microtonal music, which you'll hear in like lo-fi, where they go from 8 notes to 16 notes. You can use, like, instead of like in the key of D, you can use like D half.
Like half.
And it's so, yeah, and it's so bizarre, but it's very similar to where you can change your choices.
Yeah.
In Western music and Eastern music.
That's interesting. I was not aware of that. That's pretty cool. That seems like that'd be hard because we have problems with metric. Like our system is we use what, imperial here? Everything's feet, miles, and then you go anywhere else in the world and it's the metric, right? We're going to talk about that later. In this class, we're going to do conversions at the end. That's not the same because imperial and metric are like completely different animals. Like 1 mile is not 1 kilometer, right? But with notes, you're just like adding more resolution to it, right? So you can break it down in between. You've got something in between. All right, cool. All right, so I think that concludes the idea of sketching exponential functions. You have the idea of how to sketch them, that you're either going to have growth or decay, and that we're always going to make a t-table. And what numbers are we always going to put in there? Which ones? We're all going to agree because we could do anything, but we're all going to agree to put what numbers in there? -3, -2, -1, 0, 1, 2, 3. Okay, if you do that, I'll make sure on the test everything works out nice for you, okay? All right, that's it. That's it for sketching exponential functions. The next thing we'd like to do is actually see an application. Like, let's see where exponential functions are used. All right, so we're going to now talk about simple interest. Simple interest. And I like this topic because it gives us an opportunity to talk about things that actually might be kind of relevant to you, all right? So, there's a lot of talk in the news right now about banks, right? There's been some turmoil in the banks lately. So how do banks work? You have people over here, right? You've got all these people over here that have money, right? And when I say have money, I mean they have income, they've got enough money to put some money in the bank, right? Save some money, they can put money away. They always have a positive balance in their checking account, savings account, right? So you got people who have money over here. And you got people over here, right, who need money, right? And the bank is like the intermediate person between these two. What happens is these people say, hey, I've got this money, I'm not spending it, so I need to put it somewhere, right? And one easy thing to do is just put it in the bank. So they deposit their money in the bank and it's sitting there in an account, right? It's sitting there, right? At least when you bring up the app, it shows your balance right there and hopefully it's positive, right? And that's money that's supposed to be in the bank. You should be able to walk into the bank on any given day and say, give me all my money. And they should be able to hand you all your money, right? That's, in theory, what should happen. Well, the bank, what they do is they say, hey, look, if you leave your money with us, we're going to pay you for your money. So if you give us $1,000, every month we're going to give you 30 cents. it's a small amount of money, right, that they give you. But just to have your money sitting there, they'll give you a little bit of money, all right? And when I say that, it's like a very small percentage. Maybe the percentage, I'm not sure, I don't keep up on these rates, but I'm pretty sure it's below 1%. But I'm going to go big and I'm going to say 1%. So they say, look, you give us your money, we're going to give you 1% back every month for your money, all right? And they have all this money sitting in there, right? That these people can come get anytime they want. And what they do is they turn around and they say, oh, you need money. We have money, we have their money. And so what we're going to do is we're going to loan you their money. And then they're going to charge you to borrow that money. But they're not going to charge you 1%, they're going to charge you, well, it depends on how you're borrowing the money, right? If it's for a home loan, it's going to be around 5%. If it's for a car, it's going to be a different percent. If it's a credit card, it's going to be very high, right? Anyone know what the interest rates on credit cards are? Ridiculous. Yeah. I mean, above 15. So you're probably 15 to 25%. So I'm going to go with 25%, right? Does anyone know what affects that rate? Like how you can get that lower? Your credit score. You all know what your credit score is? No, if you don't, you should pay attention because it matters, okay? Your credit score, all of us basically start at like a 0, okay? Like we have no credit. Credit is basically you demonstrating the ability to pay bills and to be responsible, all right? And so the credit scores, your credit score, the higher it is, the more trustworthy you've shown you can be as far as paying things back. So if you have a really high credit score, you can get a lower interest rate. But if you're just like, You know, a student in college, you're working your second job, you've never had a car payment, you've never demonstrated to anybody that you can actually pay a bill on time over and over and over, then you are going to have a very low credit score, and they're going to still loan you money most of the time, but your interest rate's going to be really high because it's a risk for them. It's a huge risk, right? You haven't proven yourself. So even to, I mean, like, this isn't, I'm not bragging, this is not bragging. I have a very high credit score, very, very high. Almost as high as you can possibly get on the scale, all right? And what's that? It's, no, I mean, I haven't done anything but paid my bills. I mean, that's all I've done is paid my bills, you know? Like, I've never been defaulted on anything, I've never been late, you know what I mean? So all I've done is ever paid my bills. Any debt I've taken out, I've paid it back. And so I have a very high credit score. Even with my credit score, I can only get credit cards at like 17%. I mean, and that's with a great credit score. So I can't imagine what it is for people who are just starting, trying to establish their credit score. So anyway, okay, you get the idea here, right? You get the idea. It costs you a lot of money to borrow money, right? And so these people start paying back, hopefully, and the bank is making money, right? Because they are using their money to loan it to these people, and they're getting all this interest back and only giving them 1% back, and so there's their profit, right? So what happened recently in, where was it, California? Silicon Valley, is that there was a bank that something happened, I don't know all the details, but all the people said, hey, give us our money. And the bank's like, shit, we don't have it, you know? And so it basically, it was a big disaster, right? So like if everybody went looking for their money on the same day, it would be a catastrophe, like an absolute catastrophe. And our federal government will insure your money. The bank has to be what's called FDIC insured, so that means that the federal government has said, hey, look, up to a certain amount of money, we guarantee even if the bank collapses, the federal government will give you your money back. So that's why when you choose a bank, you should make sure that they are FDIC insured, because that way if something goes south on you, your money's not gone. And usually it's up to, I think, $250,000 that they'll insure. So, okay, this is not an economics class. This is not a financial advising class, all right? This is just for you to get to understand the way banks work, right? So, and it's definitely a little more complicated than this, but this just gives you the general basic idea. So what I'd like to do with our talk of exponential functions is I'd like to talk about the formula that banks use in order to determine how much you eventually have to owe back to them, all right? And so we have this thing called simple interest. It's the way to calculate how much money you would owe after a certain amount of time. Or you can look at it the other way. If you actually like put your money into the bank, it'll show you how much money you would have in there as it grows after a certain amount of time, all right? So here's the formula. The formula looks like this. A equals P times E raised to the R times T.